Hey, Alex, quantum computing. Sounds incredible, right? But I've heard this, inconvenient truth about its energy demands. What's really the core issue?
Heidi, you're spot on. The biggest energy guzzler, especially for superconducting quantum computers, is extreme cryogenic cooling. We're talking temperatures thousands of times colder than space, like 15 millikelvin, just to keep fragile quantum states stable. It's an insane requirement, frankly.
Wow, 15 millikelvin. That's mind-bogglingly cold. I mean, how much energy does that even take to get something that cold? Is it like a little fan or something massive?
Oh, it's far from a little fan. It requires sophisticated machinery like pulse tube coolers and dilution refrigerators, and these suck up a lot of power. A single dilution refrigerator can consume up to 25 kilowatts. That's, like running 25 high-powered air conditioners nonstop. Unlike regular data centers, for quantum, it's the cooling that really dominates the power bill.
Wow, 25 kilowatts for one cooling machine. That's really significant. So, as these quantum computers scale up, from NISQ devices to bigger fault-tolerant systems, does that energy demand for cooling just explode?
Absolutely, Heidi. As we scale to millions of physical qubits, the energy demands for cooling are projected to increase dramatically. More qubits mean more control electronics generating heat, and error correction further escalates cooling requirements. It's a massive challenge.
So, scaling means exponentially more energy for cooling. What about other types of quantum computers, like neutral atom systems? Do they face the same scaling energy problem?
Even those alternatives are expected to see rising power usage as they scale. While they might reduce some cryogenic needs, they still have significant energy demands. Pascal's neutral atom processor, for instance, uses around 2.6 kilowatts, with half for lasers. So scaling always brings increased power demands.
Okay, so cooling and scaling are big issues. But is that it? What about the energy to actually make these complex quantum systems? Is there a hidden cost in manufacturing too?
Oh, you've definitely hit on embodied energy. Beyond just running them, manufacturing quantum systems and even classical chips is incredibly energy intensive. Processes like EUV lithography demand enormous amounts of power. In some cases, the energy to manufacture a chip can even exceed its lifetime operational energy.
Wow, that's wild. The energy to build it is more than to run it. And quantum also relies on specialized, rare materials, right? Does their production add to this embodied energy footprint?
Absolutely. Quantum uses specialized and often rare materials like niobium and tantalum. Their extraction and refining are incredibly energy-intensive processes. If quantum reaches a million qubit scale, this embodied energy could become a substantial bottleneck for sustainability, underscoring the need for greener practices.
So it sounds like quantum has a huge energy problem, but I've also heard it could actually help with global decarbonization. That sounds like a total paradox. How can something so power hungry be good for the environment?
It's totally a duality, Heidi. You're right. Despite these challenges, quantum computing holds immense potential for decarbonization. Quantum algorithms are anticipated to optimize energy grids, leading to reduced waste and improved distribution. They can enhance renewable energy integration by modeling consumption patterns, facilitating smarter grid management. It's a powerful tool, really.
That's fascinating. Optimizing grids and renewables? What else? Can it help us discover new, greener technologies too?
Absolutely. Quantum computing can accelerate the discovery and design of sustainable materials for critical applications. Think improved batteries or carbon capture technologies. And it can lead to more environmentally friendly chemical processes. By simulating molecular structures and reactions with unprecedented accuracy, quantum computers can help identify new catalysts and compounds that reduce waste and energy consumption in industrial processes. It's a huge upside.
So there's a huge potential for good, which is great, but what are researchers doing right now to actually address quantum's own energy wall? Are there like specific initiatives to make them more sustainable?
Oh, tons of initiatives are underway. We're seeing a big push for more efficient cryogenics, like magnetic cooling, and hybrid architectures are being explored to use quantum hardware only when essential. Also, energy-aware algorithms and carbon-aware quantum scheduling aim to run jobs during renewable energy peaks or in low-carbon regions.
Wow, so a lot of different angles. It sounds like they're really tackling this head on. But how does the energy consumption, even with these efforts, compare to traditional supercomputers for complex problems? Is quantum still, like, way more energy intensive?
Not always. While current quantum systems have modest power footprints, studies show that for specific, intractable problems, quantum computers can achieve solutions with significantly less energy than classical supercomputers. Some reports suggest quantum can be 100 times more energy efficient for certain tasks. So, for the right problems, it offers a substantial long-term energy